Data, like oxygen, is everywhere. We need data to run critical systems that support us, educate us, drive our businesses and financial affairs, and record our activities and progress in our endless pursuit to improve the world around us. With so much data to manage and store, the issues around compression is a long-studied challenge, particularly when working across enormous analytical systems. To address this issue, a team of data scientists and researchers from different sectors was put together by IBM Almaden Research Center in California. Their results have been very positive. Join us as we meet one of the authors, Matthias Boehm, professor at Graz University of Technology, Institute of Interactive Systems and Data Science, who explains a bit more about this work.
The key idea of this work on compressed linear algebra is essentially to apply lightweight database compression techniques to numeric matrices and perform linear algebra operations such as matrix vector multiplication directly over the compressed representation. So for traditional machine learning algorithms that heavily rely on matrix vector multiplication, those workloads are often memory bandwidth bound and not compute bound. Because they are memory bandwidth bound, compressing with a substantial compression ratio those matrices allows us to reduce the memory bandwidth requirements and potentially fit larger data sets in available memory.
The research took a unique combination of existing techniques, such as aggregation and sampling, and then adopted them for numeric matrix representations. In this approach, compression ratios and performance times are significantly improved over traditional standard approaches.
Now this applies to a single node setup where you just want to keep the entire data set in this one single node's memory. It can apply to hardware accelerator devices such as GPUs that have usually very limited device memory. And third, it applies to large-scale distributed data parallel computation, essentially a number of different applications and number of different data sets, which is essentially a strength of this approach, that it's not just specific to one particular data set. This work is an excellent example of essentially doing research in the intersection between industrial applications, building an actual machine learning system, and doing cutting, bleeding edge research. And one of the lessons that was incredibly beneficial for us was really the separation out of developing algorithms and doing optimizations, including compressed linear algebra, under the covers in a transparent manner for a user.
Find out more in the Research Highlights article, Compressed Linear Algebra for Declarative Large-Scale Machine, in the May 2019 communications of the ACM.